Dear colleagues, today we are going to talk about the positive effects of the smart energy systems integration on grid stability and resilience, especially for low inertia systems with high penetration of renewable energy. Home systems that constitute a distributed generation and storage may be utilized for a demand-side load shedding and frequency support in case of major disturbance in the grid. Such events may occur during extreme weather conditions, power plant equipment failure, cyber-physical attacks on grid infrastructure, and more. First, I will outline the concept, the formal representation, the modeling approach, and of course the results and conclusions will be discussed. So, how we can support the grid in case of major disturbance? Well, the equipment may determine that the grid is going to dangerous direction. So, if the frequency is going to levels when the protective mechanism will be engaged, for European grid it's 49 Hz, our equipment, smart equipment, may decide to disconnect from the grid and relieve this load from the system. It will help to stabilize the frequency, and in short duration of time we may return to normal levels and reconnect to a grid. For a home system that typically have battery from 24 to 36 hours of reserve power, minutes or even hours of operating without a grid is not a problem. It will not create any inconvenience for a user. It will not create any problems in sense of resource of battery. It's absolutely normal condition for our equipment, but for a grid it may be crucial. So how we define this formally? We have our bottom line. Our bottom line is where the load shedding starts in the grid. It's 49 Hz for Europe. And we start in slightly above this level to disconnect inverters that are drawing most power. So according to this formula, if you drawing closer to your contract amount, you will be disconnected slightly earlier. If you are drawing very little power, you will not disconnect until 49 Hz. Of course, there is some deviation, some noise that is present in the equipment. It also contributes to a task that not everybody will be disconnected at once. So it also will be very elastic for the grid. So it also will improve. And of course, there is a reconnect logic that contains a hysteresis to make sure that we really reconnect only when the grid is healthy. And of course, the state of charge of our battery should also be taken into account. There is a delay, a random delay, that will additionally protect system from reconnecting all at once. If all systems has been disconnected, they should not be reconnected at the same time, even if the grid is very healthy. So there is an algorithm to prevent this sudden return of this load. How we can verify if this approach will contribute to stability, will help us, will maybe make things worse? We have conducted a series of calculations using a PPSA Euro project, modeling suite. The system under investigation was Italy because it has very high renewable energy penetration. Because of this, the system have very low inertia. So if some disturbance happens, the system will react very quickly, and protection may not be engaged properly, that will show us if this approach that proposed, if it will actually help grid or how it will be behave. The modeling software is PPSA Euro project, calculated using 160 clusters with 1 hour resolution for analysis of power flow, and with further calculating the frequency response if disturbance happens. So it was calculated for winter evening peak consumption without solar almost. So it is close to worst case scenario how system will behave. The frequency response plots for traditional protection mechanisms, its base scenario. We have nadir around 48, 56 hertz. So we hit in a little bit a shedding mechanism, probably maybe 10, maybe 20% of load will be shedded. So disconnection will happen for consumers that may not have a backup. So the quality of service will be reduced, but not catastrophic situation. But obviously we need to try to avoid such situations. So the response is typical when the primary response is engaged and governor increase generation on our thermal power plant. The situation start to normalize with some oscillations, obviously. What we see when we use the logic where some customers will disconnect from the grid. In Italy, there is around 700,000 of households that have solar systems operating behind the meter. They not producing power, not contributing. They just have a generation and use it for own needs. So if these 700 customers will trip and disconnect from the grid, we are seeing that the nadir is a little bit higher, and it only barely touches the first tripping level. So it's maybe 10% of traditional shedding mechanism will be shedded, maybe nothing. So it's a not definitive answer. It depends on multiple factors, and if we are lucky, we will completely go through this event without shedding, only with systems that has been tripped and go to battery backup. So as we can see, the effect is much milder. The shock is 2 gigawatts of lost thermal generation. It may be also a case when you lose import from other countries. So it's a typical shock that may occur during thermal power plant disconnection or disconnection of import from Switzerland or from France. That will create such disturbance. So we can see that even this small measure, disconnection of relatively small number of customers that will not actually feel the problem, already helps the system to become more stable. How we can implement this in practice? There's a lot of old equipment that will not be replaced in near future. We may create standards for the future, for more advanced, more recent implementations, but how we can deal with equipment that is already deployed and already in use. We can create a control module that will integrate with some sort of smart home solution. We use a home assistant for prototyping. And this control module will basically decide, as the conditions are met for our to trip, as the conditions are met for our to reconnect. So it should have a metering capabilities to measure the frequency of network. In some implementations, it may have a calculation for rate of frequency change as well, and voltage, obviously, take into account. But most important characteristic is frequency. So first of all, we measuring frequency, and we communicating with our inverter. It may be different models, different manufacturers, but they are mostly it's not very complex task. With Popular, we have a pretty easy interconnect. With some more outdated, maybe there are problems, but still it's not a big problem technically. So this simple approach gives us ability to dump the shock and improve resilience of our energy grid. So what we can tell from these simulations, we have more of them that involve electric vehicle charging stations that should also follow. But the idea that we may utilize behind the meter load as a dumping capacity is very, very important and may contribute to energy resilience, especially for the cases when we are hitting the high impact, low probability event. So what conclusions we can get from these calculations? The calculations are preliminary, and we will continue to calculate for other countries and other conditions. How effective is the strategy, where we should put our tripping frequencies. For now, it's half of hertz, above 49 hertz. So from 49.5 till 49. 49, this fleet will be completely disconnected from a demand side. So with higher penetration of renewable energy, there will be required more advanced techniques to prevent cascading events, to prevent some oscillations, dangerous, and how to improve energy resilience. And it may be achieved on a smart home side. It may be achieved on using demand-side emergency support. If we develop protocols, if we make them standard, and maybe some regulation may be required to improve how quickly this technology will be adopted. It is shown that the demand-side emergency support is highly effective because it can be applied quickly and without serious implications for consumer quality of service. It's most important. So the remaining problems in this area, how we see it, especially when we're talking about high impact events, it's a limited situational awareness. So we cannot use the centralized systems when we will control remotely our fleet. This approach is working for economy, so we can be provider of auxiliary services. That works, but when the extreme weather conditions or cyber physical attack or some other serious level of event will happen, it's probably that this capability will be down and will not work, and that's a threat. So from our point of view, it is important to implement bulletproof solutions that will work no matter what. So this is all for today's talk. Thank you so much for your kind attention.